Hey, my name is Michael Blaine Hewling. I'm in Lab Section M06, and this is Lab 7, the Black Hole Mass Lab. The observation was the movement of a sun around a black hole rendered in Python, and the result was that the mass of an unknown black hole can be calculated based on the position data of an object moving around it and the composition forces acting on that object. For this week's video, we were asked to take the program which we created in lab last Wednesday and essentially just run it for a new set of data for a star's position with a new black hole and that at a new position. We start with some initial conditions like the star's mass, which is 1.989 e to the 30, and a time step which is equivalent to 1 day in seconds. We change the program that it is pulling the data from to the new data set we got from WebAssign, and continue to set the conditions that are going to be taking the star's x and y conditions. We come down here, and using the momentum principle, we can calculate our velocity final and velocity initial based off of the star's position data, and then we can calculate our momentum initial and momentum final based off of the velocity data we just gathered. From here, we can solve a delta v and a delta p by taking the velocity final minus velocity initial and momentum final minus momentum initial, which we can then use to calculate a dp dt, which is going to be our change in momentum over our change in time. This also happens to be equal to our fnet, which we set here. Now, to calculate for the curving motion, we need to solve for fnet of parallel components and fnet of perpendicular components, as well as dp dt of these components. Then we create three arrows, one of which will show our fnet, one shows fnet parallel, the other showing fnet perpendicular. And finally, we will calculate the mass of the black hole by taking its position, setting g, and then solving for the mass based on the idea used to find gravity between two objects here. And when we run the program, looks like this. You can see the arrows of fnet, perpendicular, and parallel as it curves about what the black hole is somewhere in here. Then we come back to our output data, and we have the mass of the black hole is 3.566 e to the 31 kilograms. The what does it mean question wants us to compare fnet and dp dt and see how they are similar and different. The fnet is the total force that is acting on the object, and the fnet parallel and perpendicular are essentially just the two components that create this force. One, the fnet parallel, moves in the direction of the momentum, or p hat, and the fnet perpendicular goes in the n hat direction towards the center of what you're rotating around. Now, just like fnet, dp dt and its parallel components are related because the parallel and perpendicular essentially just come together to form the total net component, or the total dp dt. And because they're the same in such ways, you can see that dp dt and fnet are pretty much equal in value. However, the fnet and dp dt value differ because although they are the same value of number, the fnet is the total accumulation of force that is acting on an object and causing it to move in the way that it does. However, the dp dt is just showing your change in position over a set amount of time, which shows the motion that it has traveled in that set period, which happens to be equal to the fnet. So they are not the same thing. Fnet is your total force acting on the object, and dp dt is essentially just a short-time representation of that force. Now, coming back to Python and slowing down the rate, we can run the program again and see how the arrows work a little better. So when you run it again, you can see that one arrow is moving parallel towards the momentum, the other is moving perpendicular, and the black arrow, which is your fnet, is pointing towards the center at which you are rotating around. The what if question says, imagine if the black hole whose mass you found was replaced by a different black hole, but still placed in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? The answer is yes, you could tell the difference. Since gravitational force is the only one acting upon the star, and the fact that it is approximated using mass and distance of two objects from one another. Since the black hole is at the same position, the distance between the two doesn't change. And if its mass were to change enough, the net force on the star would be altered. Even if the motion stayed the same, the distance of that motion would be altered by the change in force, because a greater force is going to have a greater gravitational pull, creating the net force stronger and altering the movement of the star, whereas a lesser mass would create a lesser gravitational force, which in turn would reduce the force on the star. And that's it for this week's lab report.